Requires double clicking on this computer. I have no idea why, but there we go. So you only click once, it's like, I don't know what you're talking about. So today is Wednesday and the date is April 5th. And we're going to talk a little bit about statics, since that's a class that we're doing today. This is our Moodle page for statics. And we are way past spring break, which is really exciting. We're almost 3/4 of the way done with this semester, which is really unbelievable. So if we take a look at our dates for April 5th, today we should, in a perfect world, be turning in homework for chapter 8. But of course, we don't live in a perfect world, so some of you will be there and some of you will not be there. So we may be working on chapter 6 or chapter 7, and we'll take a look at that. So anyway, chapter 6, we talk about analysis of structures. In class, I did a problem using the method of joints. I did not ever do a method of section problems, but I've reviewed your homework and it looked like everybody was sort of getting up to speed with that. If anybody needs help with the method of sections, let me know and I'll take care of that. And so then if we were working through chapter 7, we're talking about internal forces and moments. We only did part of chapter 7, section 7.1 through 7.3. And just like with chapter 6, chapter 7 is a direct precursor to a course you'll take next year called Mechanics of Materials. So everything that you learn in 6 and 7 will give you that good foundation for Mechanics of Materials that you take that next year. And then chapter 8, we're talking about friction. So after we get through with the homework for chapter 8, there's a quiz that's over sections 6 through 8. And I don't think anyone's turned this in yet. Let's take a peek here. I won't show your names. It's just the numbers. Nope, don't have any turns in yet. Okay. So once again, with the quiz for chapters 6, 7, and 8, it's the same as it was for the quiz with chapters 1 and 2, where you'll take the quiz here, or you'll pull up the quiz here, but you'll actually work it out on paper and then submit your written work through this link. Okay. And or not this link, sorry, this link right here. That's better. All right. So so that's sort of where we are right now. What would you guys like to do today? Do you want me to work a problem in chapter 7 and chapter 8? Is there anything in particular that's got your attention that you'd like to talk about?
I don't know. I felt the bending moment.
Oh, yes. Okay. Bending moment diagrams are kind of weird. That's right. So did you have specific questions or just want to talk about it a little bit?
Just kind of talk about conceptually.
Yes. Yeah, well, and that's good. I mean, it's a really complicated topic, and it's something that, like I said, you'll delve into quite a bit more when you are in Mechanics of Materials. But for now, we sort of touch on this idea of a bending moment diagram in sort of a, I don't think it's any easier than what you do in Mechanics of Materials, but it's more foundational at this point. So basically, here's an idea, and then I'll work a couple of problems. But if you have a beam that's supported on both ends, and you may have noticed, I think we talked about this, that this indicates a fixed support and this indicates a rolling support, which is really important to not keep things in a bind, okay? If you have a force acting halfway down here, you could say if this distance is equal to this distance, that this force, the reactive force here is going to be force over 2, and the reactive force here is going to be the force over 2, just by symmetry. Now, depending on the placement of this, or whether it's a distributed force or whatever, that's not necessarily the case, but this is like a simple case. When we talk about both shear and bending moment diagrams, what we're really looking at is this idea that depending on how a structural member like this is loaded, we want to know where it's going to fail. Because if you think about it, once something fails, we don't have a structural member at all, right? We just have a pile of garbage. So we want, we have pieces, that's exactly right. So what we're really interested in is not, I mean, we're interested in how the forces and moments are distributed, but we're also interested in where that failure is going to occur. And so there are two key components to that, where failure occurs. Okay, one is going to be where the structural member is weakest. And that could be due to the material or the size, and where the load is greatest. Okay, so we're really addressing this question with the shear and moment diagrams. Now, the other thing about it is that shear tends to concentrate, and specifically, it often concentrates on fasteners. So in other words, if you have a cross-sectional area of a beam that looks like this, okay, but if you have spliced something together and you screw it or bolt it together, the shear is actually going to concentrate right here. Bending moments are a little bit different. Bending moments tend to distribute a little bit more. But in other words, we want to be able to see how that distribution occurs. Now, if you look at something like this, if you push on it right here, what you can see is that this is greatly exaggerated, but this sort of a loading configuration would convert it. Yeah, make it into, like I always like to say, a smiley face, right? So it'll bend it this way. If you had it loaded the opposite way, it would bend this way. All right. So what that really does is it tells you that somewhere in the middle of this beam, the length, which we're just going to call L, is going to equal the length up here. Okay. But in this configuration, the length up here is going to be some length that's shorter because it's in compression. And the length down here is going to be somewhat longer and it's going to be in tension. So another property of certain materials that we find is some materials are very homotropic. In other words, they bear load the same way in two directions. Other materials are isotropic. For example, concrete bears compression very, very well, and it does not bear tension basically at all, which is why if you ever see like a large floor of a shop, for example, there'll often be rebar in the bottom. They don't put it in the top half because if you're loading it from the top and the top is in compression, this is referred to as the neutral axis. Everything above this is in compression, and concrete works really well that way. Below the dam, not so much. It's also another example of this is if you look at a dam, like a concrete dam, if you look at it in side view, dams tend to be built like this. Okay, this is like the top. This is the water surface, which they use a little symbol like that, just meaning that's where the water and the air interface each other. And then it gets bigger and bigger as it goes down. The reason for that is water becomes heavier. Water acts under its own weight. So the farther down you go, the more pressure you encounter, and that puts more pressure on the dam at lower, not elevations, at greater depths. The greater the depth, the higher the pressure on the dam. So it has to be bigger at the bottom. Now, the other part, if you look at a dam from a top view, you'll see that dams are usually curved like this. Okay. And if you go to the Buffalo Bill Dam, for example, and if you look over, aha, yes, he's seen this. So what you'll see down here, you'll see some structures, and then you'll see the little piece of the river and maybe a spillway or two pouring out. But the bulk of it's convex facing the water. So from this little diagram, why do you think that is?
Yes.
Yes. That's exactly right. What happens here, just like you've said, is the water puts this piece into compression, which is,
Another way.
it would splay it out. That's exactly correct. So if the dam was built like this and the water was pushing this way, it would naturally be pushing everything apart, which is exactly the wrong thing to do for concrete. So in combining, when we work with, when we start getting into mechanics of materials next year, or whenever you take mechanics of materials, this will be something that you'll talk about the isotropic and anisotropic properties of different building materials. Okay. Now, for now, what we also need to do is determine where the forces are going to be the greatest. Okay. So we focus on if we have this type of a load. So in other words, if this is axis, these are called axial loads. And once again, if this is the axis, this is called transverse load. So it's just a geometric term. When we're talking about transverse loads like this could be something like, if this were a footbridge, this could be people walking across the bridge, right? Somebody standing in the middle. Good morning, afternoon. It's afternoon. Sorry about that. So if you have people walking across it, this is a very common kind of a configuration. If you have a bridge that traffic is going across, very common kind of configuration. There's lots of other more complicated things, like when we talked about trusses and we talked about how loads are built in, how loads are distributed among the structural members and trusses. If you have something that has the ability or the propensity to bear a great deal of a load, like for example, I'm going to draw my conception of what a house looks like, okay? Please forgive me, anybody who actually has lived in a house, you'll know that this is quite simplistic. Okay, what happens with a house? Well, if you have wind blowing on the roof, that's going to tend to push this way, which is going to tend to push the walls this way, which tends to make everything fall down, which is a terrible idea. So that's where all these trusses come in, where you put in members and cross members so that the load is distributed among those different cross members and so forth. But that's the ideas that we're getting at when we start talking about bending moment diagrams and shear diagrams. So basically, when let me get a problem out of the textbook and I'll just start to work it as I talk through these ideas. Okay, you generally use bending moment and shear diagrams in concert with each other because you're interested in both. Okay, now shear, which is generally assigned the letter V. Okay, I don't know why, nobody asked me. And the bending moment, which is given the letter M. Okay, shear results in a shearing force. And shearing force is distributed, like I said, tends to be with connectors. Moments, on the other hand, lead to normal forces, which normal stress is assigned the letter sigma. Okay, so in other words, what a bending moment tends to do is to pull something apart or push it together, tension or compression, whereas a shear tends to make things slide off and slide away from each other. Okay, so what we're doing then is we're looking at how things are being rendered apart in one direction, how things are being rendered apart in another direction, and those two directions are perpendicular to each other. Doesn't matter if they're X, Y, or if they're at some skewed angle, but they're perpendicular to each other because of classification, but also because of Pythagorean theorem. Right angles equal easier, no law of cosine. Yes.
Yeah. So you said the bending moment before tension and compression.
Yes.
It's rotating into itself like this.
Exactly.
Or is it rotating against itself, or both?
It could be both. Right. So, and that's what the bending moment diagrams, that's where we're getting to when we start talking about bending diagrams.
It looks like it's holding it.
Yes.
Trying to break them. Right?
Yes, yes. Okay, that's
not put it into it.
right. And that has to do, and that's an excellent point. That has to do with the sign convention. And I will start by telling you that the sign convention in different books and different textbooks is not 100% consistent. So for you, it's important to use something that's 100% consistent, and then it's easier for you. Then if it's backward, you always know it's backward from what you drew rather than backward from, I don't know what, right? So this is like a little organizational point. But so if we take a problem, and I'd like a problem with some numbers in it, instead of L over 2, blah, blah, blah. All right, let's take a look at problem 736. I don't know if that was one of your homework problems or not. But 736 looks like this. We have a fixed support at A, we have a rolling support at B, and we have 3 loads applied at intermittent distances. Is this a problem that you had for homework? Because I love this problem, so I figured I probably assigned it, but I couldn't remember. All right, so if we draw this, the first, it's always a series. This is, now we've talked about the theory or the reason that we do this. Next thing that we're going to do is just talk about execution. How do you work these problems consistently every single time to be correct? Okay, so if we start here and we have fixed support at A, rolling support at B, and we have a beam that extends from point A to point B, and we have 3 loads at different distances. We have a 16 kilonewton, 32 kilonewton, 40 kilonewton, and we have C, D, and E. Okay, so we have 5 identified points. The distance from here to here is 0.6 meters. Distance from here to here is 1.5 meters. And the distance, oh, I'm sorry, 0.9 meters. Yeah, this one's 1.5 meters. And then this is from E to B is 0.2 meters. Okay. All right. So what happens here? Well, there's 3 things that we need to do. The first is to draw a free body diagram. Poof, free body diagram. The second is to do a shear diagram. And the third is to do a bending moment diagram. Okay. Now, we can draw a free body diagram, but that's where we always begin. And the best way to do these is to always stack them on top of each other and have the same lengths. So once again, that's just a technique. You can organize that information other ways, but as we're learning to communicate graphically and mathematically with each other, it's kind of an important thing so that somebody can look at that and just see it rather than reading a paragraph of your writing that says, and 0.5 meters in, we have a discontinuity and blah, blah, blah. You know, you draw the picture, everybody sees the data. All right, so to do the free body diagram, I chose this because it will go really quickly. We have points A and points B. So we have the force at A acting up and the force at B acting up. So those are both positive. And then we have 3 forces acting down. So we have minus 40 kilonewtons, minus 32 kilonewtons, minus 16 kilonewtons, all together equals 0. Okay, so then we have the force at A plus the force at B is equal to the sum of these 3 things when we bring it over to the other side. So it's 72, 78, 88 kilonewtons. Okay, but we don't have any reason to think that it's going to be divided equally between A and B, right? So we have to do moments in order to find out what the force is at point A or point B. Then we could use this equation to determine the other. So this comes from summation forces y equals 0. The other thing I've left out, but there's no forces in the x direction here. If there was an applied load over here, for example, it would have to be taken up at A, wouldn't it? But we don't have anything like that going on. So since everything is vertical, and this is the only thing that will bear a horizontal, this is the only thing that will bear a horizontal force, we don't have anything happening there. Okay, so next thing we need to do is to take the moments about one of these points, let's say A, equal to 0, in order to determine what that reactive force at B is. So we get 40 kilonewtons times 0.6 meters, because that's the distance from point A. And we see that that rotation, if I put a pin here, this would rotate it clockwise, which is a negative moment. Once again, that's a sign convention. It's not 100% used, but you should always use the same sign convention. In our book, to go along with the right-hand rule, we tend to say that a clockwise spin in a 2-dimensional plane is negative and a counterclockwise spin is positive. All right, same with the 32. It's going to be clockwise. Here we have 0.6 plus 0.9, so 1.5 meters. Last but not least, on my applied loads, we have 16 kilonewtons times this entire distance, which is 3. And then here, if you look at B is pushing up, so that's going to be counterclockwise. So positive, the force at B times the entire distance, which is 3.2 meters, equals 0. Oops, there we go. All right, so if we look at this, we can say then the force of B, I'm going to pull everything else over to the other side, so they'll all become positive, and then divide by 3.2. So I get 40 times 0.6. I can put that here so you can see that 40 times 0.6 plus 32 times 1.5 plus 16 times 3 equals, that's 120. 120 divided by 3.2 is 37.5 kilonewtons. So we know that this is 37.5 kilonewtons. We know from this equation that the force at A is going to be 88 minus 37.5, which is force at A is equal to 50.5 kilonewtons. Okay, so now we have enough to do our free body diagram, which is the first of these three. Okay, so I'm going to kind of leave this for my clean space where I'm going to do all my stuff. First being the free body diagram. Here we have point A. Here we have point B. Those are both represented by forces acting vertically upward. F at A is 50.5 kilonewtons. F at B is 37.5 kilonewtons. And then we have our three forces, 40 kilonewtons, 32 kilonewtons, and 16 kilonewtons. And we also have some distances there. All right, now the next thing we want to do is a shear diagram. When we do these shear diagrams, when I work these out, first of all, I want to leave a sheet clean. This is where my answers are going to be. So I'm going to have a nice stacked 3 series of these. I draw little bitty diagrams to sort of show what they're going to look like. And the process that you really use is to cut away after an event. What can an event be? An event can be the application of a force, can be a change in the diameter. Here it's just going to be the application of a force. Okay, so we want to look first of all from where the force at A, from point A to right before this force is applied.
You said right before. So we're not actually taking into account that.
That is correct. That is absolutely correct for that first little chunk. So here we have 50.5 kilonewtons acting up over here to the next point, which is point C. I should label these so I can talk about them. Okay. So from A, let's go and do this. From here at point A to right before point C, we have a 50.5 kilonewton force acting up. Now, if you cut away this way, if you start on the left and work to the right, the sign convention that will give you the proper answers is to use V acting downward. Now you can put V acting upward. It's just that it gets a little bit strange in terms of the sign convention because you get into negative negatives. So if you use this, you can then say the summation of forces in the y direction equals 0. This is positive, 50.5 kilonewtons. This is negative, minus V equals 0. So what you get is 50.5 kilonewtons equals V for this first little part. What that means is from here to here, you have a V of 50.5 kilonewtons, and it's positive, so it's above the axis. Okay. Now what happens between C and D? Well, between C and D, you have 50.5 kilonewtons acting up. you have 40 kilonewtons acting down. And then between C and D, oops, you can't see my work here. You have, once again, V acting downward. You just call it V. So here you would say 50.5 minus 40 minus V equals 0. 10.5 minus V equals 0, or 10.5 kilonewtons equals V. Okay, so what that means is between here and here, you have a V, responsive V of 10.5 kilonewtons. Now, the other part I want to show you is there are discontinuities like this in V. This is just how V works. When something happens, everything changes really quickly. That's why connectors fail. That's why they have to be really, really strong in order to not fail. But these jumps are difficult for materials to bear. So welcome to the world, right? That's the real world. So we got to go with that. All right. So now let's take a look at the next part. From D to E, we have the force at A, which is 50.5 acting up. We have a 40 kilonewton force acting down. We have a 32 kilonewton force acting down. And before we get to point E, then we have that responsive shear of V. So doing this again, we get 50.5 minus 40 minus 32.5 minus V equals 0. If we do this, this is 10.5, 10.5 minus 32.5 is negative 22 kilonewtons minus V equals 0, or negative 22 kilonewtons equals V. Right, so that means from here to here, our V diagram looks like this, minus 22 kilonewtons. Okay, now here's another point. With shear, the sign is only directional. Okay, unless there's some weird anisotropic property of that material, a negative shear and a positive shear have the same effect. They shear the material. It's just whether it shears it this way or it shears it this way. Yes.
We write some of those forces from the other side.
Yes. Let's do the last one.
We get different results.
We would not, because you use a different sign convention. So if you start on the right and cut to the left, you would do it. Let's see. Let's go from here to here. All right, let's do that. So here, let's say that we start here at FB, right? And that value is 37.5. If you cut from here to here, oops, you can't see what I'm doing here. This time you're going to draw V upward. Okay. All right. So then when you do that, you're going to say summation forces Y equals 0, 37.5, just plus V equals 0. So you get V is equal to minus 37.5. Okay. What about from here to here? You have the force of B, which is 37.5. You have 16. And then from here to here, you have a plus V. So I think I wrote 37.5. So here you would say 37.5 minus 16 plus V equals 0. Okay. And then you would have V is equal to minus 37.5 plus 16. 37.5 negative. So that's 21.5 negative. V is equal to negative 21.5. Okay. So, and I think I've got a number wrong here somewhere, 37.5, but essentially, if I had done my math correctly, that would work. So I'm not really sure where I've got. So this is negative 22. My answer here says negative 21.5. It should be the same number. I don't really know what I did. So 37, 16, 22, 10.5, 10.5, 32. I see it too. 50.5 plus 37.5, 88 minus 40 minus 32, 16. Yeah. I got something. Did you see what I did though? But in other words, it comes out to be the same number. It's the same sign and everything, but that's why that's where the sign convention becomes important. Okay, and I would even go so far as to say, for my own work, just because if you do these things and you do them quickly, especially, it's it's good to just have a format to use. I always cut from the left to the right. But recognize, okay, let's talk about one other thing. Why do you change it? Why is it up here or down here and up on the other side? Because really the net force is 0, isn't it? I mean, there's really no force acting there or the beam would move.
So if we drew it from the right. or
Uh-huh, yes,
drawing it from the left, it would have to be up. and
Absolutely.
directly opposite.
every single time. That's correct.
And that's why the sign convention doesn't matter.
Yes, as long as you do it correctly, as long as you do it consistently. How's that? Yes. So when you start on the left and cut on the right, put your V going down. When you start from the right and cut on the left, draw your V going up. So you're sort of paying homage to the fact that really the V's are just opposing each other.
Yeah.
Yeah. They're not really moving the beam, they're just opposing each other.
Okay.
All right? Yeah. And then, just like your teacher did not do here, just make sure that you got your arithmetic correct, because I've lost or gained a half of a kilonewton somewhere along the line, but that's the price you pay. Let's take a look then. Now we've got V. Oh, I didn't finish, did I? So this would be 37. So this is negative 37. So in this part, it goes like that, right? Negative 37.5 kilonewtons. Okay, so there is my V diagram. Now, the one thing, like I said, you notice there's a lot of inconsistencies. It slips above or below the 0, and none of that really matters. It's just a magnitude and a directional thing. For a moment diagram, if we go back to my original little piece of work here, if you look at the way that these forces are applied, this is going to bend this into a smiley face, so to speak. This tends to be a positive moment, okay? But once again, we're going to cut and we're going to draw our moment going a way that's going to show a sign convention that's consistent. If we start here and cut on the right, we draw our moment like this. If you think about that, when you put a pin in this and you spin it, that's a positive moment. That is correct. Now, if you cut the other way, if you start here and go this way, you draw your moment like this. Once again, because they're opposing each other. And that doesn't mean it is going this way or it is going that way. It's just that's how your signs are going to come out without making double negatives and so forth. But this would be a negative moment, wouldn't it? Because it's spinning it clockwise. All right, so let's take a look at that piece. So, trying to decide if I want to use the same piece of paper. Still at 15 minutes, so I'm doing okay. All right, let me just redraw this then. I'm just going to just work on this free body diagram. So I'll just draw it down here. I'll put, hang on, put that on the screen. Let's do this, FA. Okay, so between A and C, I only have this distance. We need to make sure that we take into account our distances now. And I'll show you what that is. This distance is 0.6 meters. Okay. Between here and here, I draw the moment that looks like this, which is a positive moment. My value of FA is 50.5 kilonewtons. Okay, what is a moment? A moment is a force times a distance, right? Okay, so if I were halfway, if I were just a smidgen here, in other words, I'm thinking about going all the way along here. If I'm just a smidgen off to A, if I'm right at point A, the moment is going to be 0, right? Because force times distance is equal to 0 because the distance is equal to 0. In between at 0.3 meters, it's going to be 50.5 kilonewtons times 0.3 meters. And at the end, it's going to be 50.5 times 0.6 meters until we get to that next force. Okay, so what does that mean? Well, I think about a point here, for example, and then I think, what if I were to spin this way? That's going to be a negative, right? So I got negative 50.5 times the distance, which I'm just going to call X, plus M equals 0. And you see, I've honored my sign convention each and every time. So the moment from here to here is going to be 50.5 times x. But x is going to go from 0 to 0.6. So the moment is going to go from 0 up to 50.5 times 0.6, which is 30.3. And the units are going to be kilonewton meters, right? All right. Now, first of all, the thing I want you to see is that the moment is going to be positive because of this summation moments about some point x equal to 0. And it's also a number times x, which is a linear equation, right? Which means it's a straight line. Okay, so that means when I take my moment diagram, when I start here at point A and I come over here to point C, according to this equation, let me draw the rest of this here. It's going to start at 0. The moment is going to start at 0. And it's going to increase linearly until I get to a value of 30.3 kilonewton meters. Okay. Now, let's take a look at the second chunk where I'm going from point C to point D. I have 50.5 kilonewtons here. And I have this distance, which is 0.6 meters. And then I have this distance, which is going to go from 0 to 0.9 meters. There's two different ways to do this, but I'm choosing to do it this way for right now. This is 40 kilonewtons acting downward. And then to use my proper sign convention, I put my moment this way. Okay. So what do I have about some point between here and here? Well, the answer is, I can think about this two different ways. At this point, I have the full force of this moment, right? So in other words, at this point, right after point C, the moment is not being influenced by 40 kilonewtons. It's only 50.5, and it's going to have this value. So I could think of this as being the initial condition of that moment. And then the condition of the moment is going to build. Now, it's not going to build at the same rate because it's going to be influenced by this, and it's going to be influenced by this. In other words, this is creating a moment, and this is creating a moment. And the moment arms are different, aren't they? Yeah, see, that's the deal. So if I think about that, I could say my 50.5 kilonewtons. I have two different ways I can do that. I can think about this as being my 0. I can say 0.6 plus some value of x, which goes from 0 to 0.9. So I could say times 0.6, it's going to give me my initial condition, plus some x. And that value is a negative. What about this one? It's going to be positive 40 kilonewtons. Now this 0.6 doesn't figure anymore. It's just the x. That's right. Plus m equals 0. Okay. So when I do this times this, lo and behold, I get that initial condition. 50.5 times 0.6 is negative 30.3 kilonewton meters minus 50.5x plus 40x plus m equals 0. It's still there. It's still linear. It just starts at a different point. So in other words, instead of being xb or y equals, you think about y is equal to mx plus b. Before it was just y is equal to mx because b was equal to 0. Now b in that equation is 30.3. All right. And I'm also doing this because when you get into mechanics of materials, what we're doing right now is a pretty graphical way of doing this. You can also do it pretty analytically, just with equations. And so if you think about it both ways, right from the beginning, you'll be a little bit more prepared. All right. So here then I get the moment is going to be equal to 30.3, right? Because it comes over as a positive. Then this is going to come over as a positive plus 15.5x. Okay, well, when x is equal to 0, the moment is equal to 30.3. But when x is equal to 0.9, the moment is going to equal 0.9 times 15.5 plus 30.3. 44.25 kilonewton meters. All right, so we start here. And up to here, we increase, but we're not going to increase at the same slope. We've decreased the slope of that line, right? So it's still straight line, but now we're just going up to 44.25 meters or kilonewton meters. So the slope is a little bit flatter, like that. All right, now here's the good news. We don't even have to do any math, but if you look at this side, right here, since there's no overhang, there's no applied moment, we know that when we get here, the moment's going to be back to zero again. So that's kind of nice. So if we prove everything's linear, we just have to do one more section, then we can just connect the dots. Or we could do it full on the other way. All right. The other thing I want to point out here is the moment on this particular beam is forever positive. The moment's always above zero because of that bend, that compression on top, tension on bottom, neutral axis somewhere between. Okay, so let's do one more. Let's go from here to here. So if we go from here to here, and this is our new X, here we have a different moment arm. So we have 50.5 acting up 4.6 meters. Then we have 40 acting down. And this time we put in the value, which is 0.9. And then here we have 32 acting downward. And then this is where we begin our X. But the X is going to go over here to the 16, which is 1.5 meters. All right. So here's the other deal. Just in the interest of time. I'll show you that if you did this and this right to this point, you would come up with that same initial condition right here, right? All right. So now from here to here, you're adding part of this moment, and you're adding part of the, or subtracting part of this moment, and then subtracting part of this moment. Okay. So what does that look like? All right. So let's just say we have an initial condition, which we've established as being 44.25. What happens from here to here? Well, the first thing is, we're going to have 50.5. We've already taken into account the initial condition piece. So it's going to be negative 50.5 times just X, which is going to go from 1.0 to 1.5, minus this 40, it's plus, I'm sorry, because it's going counterclockwise, times this X, minus, excuse me, plus 32 times that same X plus M equals 0. All right. So what you can see then is we could factor out the X. So we could say negative 50.5 plus 40 is negative 10.5. Well, let's just do this. 72, it's easier to do that, minus 50.5. So we get 21.5. And the sign of that would be positive X equals, well, plus M equals 0. And so we get M is equal to, and this is going to be the differential M because we're taking into account that, that initial condition, minus 21.5X, where X goes from 0 to 1.5. So at 0, we're going to be right here. When we're at 1.5, it's going to decrease by 1.5 times 21.5, which is 32.25. So it looks like that. Okay. And then finally, it's just going to go from here to here. So you see how that works? So I did like 3 different things there. I did 3 different solution techniques. I did one that was purely analytical. I did one that was purely graphical, and I did one that was a fill in the blanks. So, okay. So here to here, and the other thing you could do then is check from this side, because we have a 37.5 force here acting 4.2 meters, right? And if we go from 0 to 0.2 meters, and we have a force of 37.5, take 37.5 times 0.2. 37.5 times 0.2 is 7.5. And if you take that off of that, you have 7.5. Oh, wait, that should just be 7.5. So this should be 21.540. I've got a number wrong again here, but anyway, so this is 0. What is this number is my question. When we get right to here, before we get to that point, this one's 16. Okay, so that's why it decreases at that rate. But here, if we look at it from this side, we have 37.5 moving over 0.2 meters is all. Is that right? Yep. And so 37, so if I did it that way and I draw my moment like that, and I have an X here, so this would be negative, yep, negative 37.5 times 0.2 minus M equals 0. So we get M is, oh, that's got to be a, I got something wrong with that. Yep, that's negative, isn't it? So that comes over at the other side. So 37 point, yeah, and that's 7.5 kilonewton meters. So that means that this value would be 7.5 kilonewton meters, and this would be 0.
It shouldn't be 32.
I know, I got a boo-boo there somewhere. Should be lower than that, shouldn't it? Yeah, so that's my good arithmetic when I'm trying to do things fast. So, but does that make sense in terms of the process? Okay, so
That's easier to just look at, because I think the one on the video is like L over 2 and stuff.
yeah,
And it's hard to look at it for a while.
I agree. And the book, the authors love to set them up like that and start working out with just L and L over 2s and F1 or whatever. And it's like, yes,
It's not.
P, the force is P and the length is L, and yeah, so, but this is sort of the nuts and bolts of it, so. But anyway, do you guys have any other questions now that we're out of time? So, all right.
We'll run into, what is it?